Hello everyone, welcome to Pytorch for beginners. In this notebook, we will show you how to use a fundamental data structure called Tensor in Pytorch. We'll show you how tensors are used for storing images and collections of images. We will assume that you have some familiarity with NumPy and OpenCV. For people who do not know NumPy, we will try our best to keep the explanation at a low level, but you can also check out our free course, Python for Beginners. So let's get started. First, in this notebook, if we want to install Pytorch, so you can do it using conda install -c pytorch if you are using a conda environment. If not, then you can simply install pip3 install torch. Now, if you're using Google Colab, this may not be necessary at all because Torch comes standard with Google Colab. But if you're using this notebook on your local device, then you will need to install Torch. Okay, so once you have installed Torch, the next step is to install Torch Viz. Now, Torch Viz is a visualization library. It allows you to see the computation graph of Pytorch. It also helps you debug when you have a problem. So it's very good visualization tool for Pytorch. So we are going to install that. Next, we are going to download 2 images from MNIST. So MNIST is a very standard data set, a very early data set of handwritten digits. And it's like whenever you want to create the Hello World application for deep learning, it is the classification problem on MNIST. Basically, these are handwritten digits from 0 through 9, and your job is to classify them from 0 through 9 based on what character it is, right? So we are just downloading 2 images from this MNIST data set, and we'll see what is the size of the images, etc. Okay. So next we are going to import Torch. And we are also going to import matplotlib. This is a library that is used for plotting in Jupyter Notebooks. Very, very useful library. And then we also are going to import NumPy, which is the numerical Python library. Very useful when you want to do any kind of matrix operation or vector operation. And finally, we have our friend OpenCV, the OpenCV library, which is used for, among many other things. You will see that it is extensively used whenever you want to use images or videos, especially the capturing part. Everybody uses OpenCV. All right. So, okay, we have imported all this. Next, we are going to look at the version of Torch. As you can see here, when we try to print the version of Torch, it tells us that it is Torch version 2.3.1 plus CU 121. This plus CU 121, this is basically the version of the CUDA library that it goes with. And CUDA is the library that NVIDIA has published so that people can do general purpose computing on their GPUs, right? So CUDA library version 12.1. This is what it means. This is CUDA library version 12.1. All right. Now, let's do some image conversion. We told you in the beginning that we are going to understand how this data structure called Tensor is used for various operations. Now, Tensor is nothing but the idea of matrix. If you generalize it, that's called a tensor. So think about it. When we have a list, it is an array of elements, right? Now, if you have a 2-dimensional list, right, like a grayscale image, you have values going in the x coordinate and the y coordinate. That is a matrix. Now, if you have more dimensions than 2, right, you can have a 3-dimensional matrix, which is like a color image is a 3-dimensional matrix. You have 3 planes of R, G, and B. So that's a 3-dimensional matrix. But you don't have to stop there. You can imagine you have a tensor which is more than 3 dimensions. In fact, we use tensors of 4 dimensions routinely when we process images and videos, because let's say you want to train a neural network with many images. In that case, we actually select a batch of image. We select a collection of image from the training set and send it to the GPU and use it for training the neural network. And once the result comes back, we send another batch. So this idea of processing a batch of images in one shot is very popular, and it's a very standard thing to do when we are doing AI and deep learning. All right. So let's see how we create this batch of images and convert them into Tensor. So the very first thing we are doing here is we are going to read an image, cv2.imread. When you read an image, it by default is a 3-channel image. And this, the 2 images we have read here, we had initially downloaded it using wget. So it's right there in the directory. And we can simply use cv2.imread to read those 2 images. We can also read the grayscale versions of the images directly because these are really grayscale images. They go from 0 to 1 or 0 to 255. Okay. Now we are using matplotlib. Some figures we are creating a figure using matplotlib, and then we are displaying these images in that figure, right? So you can see that it is a handwritten 0 and a handwritten 1. So once you have done that, we are going to look at the shape. What is the size of this image? And if you use this method shape, it will tell you that this image is of size 28 by 28 by 3. So 28 by 28 is the image height and width. So the image is really tiny. In fact, you can see right here, it's a tiny image. And there are 3 channels because that's the way we read the image. We can also calculate the minimum value. So np.min would give you the minimum value, and np.max will give you the maximum value in that array, right? So now we see that the minimum value is 0, the maximum value is 255 because these are 8-bit images, okay? We can also look at the grayscale, corresponding grayscale image, and you can see that it is essentially the size is 28 by 28, right? There's a single channel, so the size is 28 by 28. Now we have the image in NumPy format, and we want to convert this image into a tensor in Pytorch so that Pytorch can use it. And the way to do it is we first pass in the original image, which we read as a NumPy array. And then we are going to say that, okay, this is going to be a float 32. When an image is read in NumPy, this image is an 8-bit image, right? So we want to change it to float 32 because we are going to treat this as a number between 0 and 1, right? And when we do any numerical calculation on images, especially when we are trying to use it in a neural network, we always convert them into float 32. Otherwise, there will be loss of precision. Okay, so we passed in the original image. We said that we want to convert this image into float 32, and then we divided it by 255 because we want to represent the image from 0 through 1. So 1 is white, 0 is black, right? So it's basically easier to treat this as a floating point number. The second image also, we do the same thing. We create a tensor for both the images. And you can see if we do the shape, we try to find the shape of that. It will say that it is a tensor of size 28 by 28 by 3. Now, earlier it was NumPy format. Now it is a tensor, okay? NumPy is a different library, and obviously Pytorch is a different library. So that is why we need to do this conversion. Okay, and using the same plotting function, we can plot this image using these few lines of code. All right, again, you can also see the minimum value because we divided it by 255, the minimum value stays the same, but the maximum value here goes to 1. All right, so this is a normalized image. Now, I had mentioned that when you want to train a model, you want to actually create a batch of images, right? You want to create a collection of images which are all together processed parallelly, right? So let's use these 2 images and create a batch out of them, okay? So here we say batch tensor is torch.stack. Stack essentially means you're stacking the images in the fourth dimension. And you will see that here, if we try to find the shape of this batch, right, it says the shape is 2. This is the 2 images. And then we have the width, height, or the height, width, and the number of channels. So this is interesting, but this is actually not how Pytorch expects the image to be, right? When you are dealing with images, the typical way Pytorch expects the image to be is you first have the batch, followed by the number of channels, followed by the height, and followed by the width. So this is how they want the data to be laid out, which is different from the TensorFlow format. If people know about TensorFlow, it's a competing library. In that, you have the batch, number of batches, and then height, width, and channel, right? But because we are dealing with PyTorch, we need to swap these dimensions, okay? So the way to do it is use the permute command, right? The permute command basically swaps the dimension. Here you can see that we had 0. 0 stays at 0. We want to make sure that this 3 comes here. So we basically are moving. So this is the this is the fourth dimension, but the index is 3. So we put 3 here, and then these 2 remain in the same order. So 1 and 2, okay? So once we have done that, you can see that the shape of the tensor changes, and it is now 2 for the batches. There are 3 channels, height and width, all right? So that is, how you create tensors from images, okay? Now, let's learn how to create tensors directly from scratch, right? Not using OpenCV or NumPy to read in, an array. And you can do it by simply by doing this, right? So you can say A equals torch.once5. This is basically a row of ones, as you can see here, and you can print it. You can also create, fill everything with zeros, and this is a row. This is a single dimensional vector that it's still a tensor, but it is single dimensional, okay? Now, if you look at it, you can also do something like 1.0, 2.0, etc. And here, when you print out the tensor, you will see that it is in floating point format, right? So these ones typically may or may not be in floating point, right? But when you do 1.0, 2.0, etc., you can guarantee that they are floating point, okay? So that's a single dimensional vector. Now let's create something which is 2-dimensional. So here we do torch.zeros, and this is a 3x2 matrix. And if you print it, you can see that it is all filled with zeros. There are 2 rows and 3 columns, okay? The other way around. There are 3 rows and 2 columns. Similarly, you could do torch, you can fill it with ones. You could also initialize it with some values. So here, every row you specify using this list, and then you comma this list, right? Now you have this row followed by this row, okay? So there are various ways of specifying the tensor. And of course, if you want to take it to 3D, it's the same thing. You can generalize it. You can see that this was our 2D tensor, and then you have 2 of these 2D tensors, and that would make a 3D tensor for you, all right? So you can see the shapes of various ones. The first one was 2x2. The second one was 3x2. The third one is 2x2x2, okay? So it has 3 dimensions. Now, how do you access the element of a tensor? It is very intuitive. You basically use these square brackets and access the element. Now, if it is more than 1 dimensions, you can simply use commas and say, okay, I want the first element number 1 from the first dimension and element number 0 from the second dimension, right? So row 1, column 0. There is an alternative way of accessing the same data. You could use double brackets like this. Each one of them is in its own bracket. So that's also a valid one, right? And finally, we have, similarly for 3D tensors, you could access them one after the other, or you could put brackets around them, whichever is convenient for you. The reason we use these data structures is because they are very powerful. They give us some syntax which is very useful in extracting different parts of the tensor. So for example, you can get all elements of the tensor by simply doing this colon. And this, these operations are very similar to many different libraries. So you will find yourself at home if you have used things like NumPy, even MATLAB, etc. Right? So now here we want all elements from index 1 to 2, right? So here we can see 1 to 3. It basically indexes all the elements from 1, 2, and 3, right? And similarly, here we index, so this is an inclusive one, and this is an exclusive one. So we want all the elements from 0 all the way to 3. The fourth one is not included, okay? And then you can get the first row by just saying, okay, I want the first row, which is 0, and all the columns associated with that row. So it's essentially the first row. Similarly, you could say that I want all the columns. I want the second column. So this one is for the column and all the rows associated with that column, right? So you basically get the second column. Play around with it. If you are not familiar with this kind of notation, just a little bit, you play 5 minutes, 10 minutes with it, you will get very comfortable with it. All right. Now you can also change the data type, right? When we create a tensor, it assigns a data type to it automatically. For example, here we have created a tensor. And if you look at the data type, it says it is int64, right? And if you want to, you could also create another one. If you look at it very carefully, this looks like a very similar tensor, but we have put a dot here, right? This is 4.0, and therefore all the elements, they are treated as floating point. And now if you print the data type, you will see that the data type is float32, all right? So so there is also a way to convert the data type of a tensor. For example, here we have created a floating point tensor by putting this dot here. And then you can basically set the type for it to say, okay, I want the type to be int64. Sometimes there will be a data loss, so you have to be careful when you're moving between different kinds of data types. And now you can print these things, and you can see that the first one was float32 and the second one is int64. All right. And it's also very useful to convert a tensor from NumPy array. These are both numerical libraries, if you think about it, matrix processing libraries. Pytorch does much more, and the tensor, there is, you can see how closely related tensor and NumPy arrays are, right? They are very similar in nature. Tensor is used inside Pytorch to do a bunch of things, and it's also, it also efficiently allocates your memory to either the device, your CPU, or the GPU. So it has many additional functions that NumPy may or may not have, right? So you have to be, that's why we use Tensor for Pytorch. Okay, so, but there is an easy mechanism to do the conversion from NumPy. So here we are creating a NumPy array. We have this tensor, we had created this tensor in this step, and now we are going to change it to NumPy array. So fNumPy, if you print, it prints like a NumPy array, right? And similarly, you can take a NumPy array, which we create here, and then you can convert it to a tensor by simply saying torch.from_NumPy, and it converts it to a tensor. So it's very easy to convert from one format to another. Now let's learn some arithmetic operations on the tensors. So it's also very intuitive. There are some non-intuitive things, but if you look at most numerical libraries that deal with matrices, etc., they have this kind of architecture or this kind of syntax. So here, for example, if you have two tensors, they are the same size. If you add them, it is going to do element-wise addition, right? So here you can see it's basically doing element-wise addition, right? Similarly, you can do element-wise subtraction. You can multiply a scalar. You can multiply two tensors. But if you multiply two tensors, it will actually do pairwise, element-wise multiplication, right? So this is not matrix multiplication. This is element-wise multiplication if you use this multiplication sign. If you want to do matrix multiplication, then you have to use something called matrix multiplication, right? So you have tensor 1 and tensor 3. You're going to multiply them as matrices. So this one is a matrix multiplication. Similarly, you can divide. Each element would be divided by that number. And then also you can do element-wise division. If you use this syntax, then every element of tensor 1 will be divided by every element of tensor 2. All right. So that's simple arithmetic using tensors. We can also do something called a broadcasting, right? And this is helpful when you're doing arithmetic, when the sizes of the sizes and dimensions of the tensors you're operating on, they're not the same. For example, look at this A, right? It is a single dimension tensor, and this is a scalar, right? So technically you should not be able to add them, but that's not how it works. So if you try to add them, it will do the addition, and you will see that this 4 gets added to all the elements, right? So we get 5, 6, and 7. We started with 1, 2, 3. Okay, so that is what broadcasting looks like. It basically replicates, this 4 replicates itself so that it matches the dimension of the bigger array, and then they are able to add. The same thing applies. Let's say you have an array which has size 1 by 3, so it has 1 row and 3 columns, and you have this another one which has 3 rows and 1 column. You can still add them together. The way it works is, let's see this example, right? So you have 1, 2, 3, right? So that's 1 row, and then you have 4, 5, 6. That's a column. The columns will replicate themselves, right? 4, 5, 6, 4, 5, 6. So it will form a 3D array, a 3 by 3 array. And then the 1, 2, 3, the rows will also replicate themselves. And now when you do the addition, they basically, because of this concept called broadcasting, they replicate and then the addition happens, right? So you can see that for the first one, this gets added 1 plus 4. The second row, right, it gets added to 5, and the third row, 1 gets added to 6. And similarly, you can imagine how this 1 by 3 matrix gets transformed to 3 by 3, and there are 2 3 by 3 matrices which get added up, right? Play with it. It's actually very simple stuff. The more explaining you do it, sounds more complicated. But when you start playing with it, it is relatively, pretty straightforward. All right. So, okay, we are done with how we do arithmetic on these tensors. One other thing to remember, most of the time we don't have to deal with these things when we are dealing with general purpose programming. But when we are dealing with machine learning, right, we have this piece of hardware called GPU, right? When we are doing training of a machine learning model, this GPU is a time saver, huge time saver, because it does parallel computing. And that is why we need these specialized libraries, right? Because CPU libraries are not sufficient. They are not sufficiently fast. Even with multi-threading, they will not work out, right? We need the parallelization of the GPU. That is why, we need a quick mechanism to say that, okay, this variable that I have defined, it's actually on the GPU because I'm going to use it on the GPU. So here, if you want to specify that this tensor should reside in the CPU, you simply say, okay, this is the tensor, I define it, and then I specify the device, which is a CPU, okay? Similarly, TensorFlow, you can also specify it to run on a GPU. Here it says CUDA, again, because here we are trying to run this on an NVIDIA GPU, right? And NVIDIA GPU, whenever, usually they don't go by the name GPU, it goes by the library name CUDA, right? So whenever you see something called CUDA, it means that, okay, this is actually referring to the NVIDIA GPU, okay? So now these two are very, I mean, they are defined similarly, but they are residing on two different kinds of memory, right? One is residing on the CPU memory and one is residing on the GPU memory, right? And you know, but after that, there is pretty much, even though things happen on the GPU, you do not have to worry about how this processing is happening, right? You write the same code, whether it's a CPU or a GPU, you do not have to worry about it once you have specified that this memory, please allocate it on the GPU, okay? So there's also a mechanism of moving the data from the GPU to the CPU or from the CPU to the GPU, right? And this is the way to do it. You basically take the tensor in one kind of memory, add dot to it, and then specify the device, right? And it will copy the data over. So that's all we wanted to cover in this notebook. I hope that you get a very good sense of what tensors are, how arithmetic is done on the tensor, how you define a tensor, how you use NumPy to, how you can convert from tensor to NumPy and vice versa, and how to think about the images, how you can read an image as a NumPy array and then convert it into a tensor, and finally, how to allocate memory on the GPU versus the CPU when you're dealing with tensors, right? So it's pretty straightforward. Play around with the notebook and you will have a very good grasp of various concepts that we have covered here in just tens of minutes, right? All right, all the best. Thank you.